channel, and today I'm going to be talking about vector calculus. In this video specifically, I'm going to be talking about the divergence. I'm going to be covering what the divergence is, how to compute the divergence of a vector, and what the no magnetic monopole rule means. So let's begin. In my previous videos on vector calculus, I talked about what the divergence, curl, and gradient actually mean. The divergence essentially measures the sources or the sinks of a vector. The source essentially means just when all of the vectors are pointing outwards. The sinks are essentially the opposite, they're pointing inwards. So that's what they mean. But to really understand what the divergence, curl, and gradient, and especially the divergence is to understand what partial derivatives are. I'm going to be giving a brief explanation on what partial derivatives are. If you want to learn more, please visit my video on partial derivatives. So the main principle of partial derivatives is to treat other variables as constants. That's the whole idea of partial derivatives. So say you're taking a derivative, and remember for the partial derivative symbol, we have to use these curly d's, but let's just say you're taking the regular derivative with respect to x of, let's just say, 5xy. Now normally you would use implicit differentiation, but sometimes for purposes in physics or other purposes in mathematics, we really don't want to use implicit differentiation. And by the way, if you want to learn more about implicit differentiation, please visit my video on implicit differentiation. Okay, so as I mentioned, in physics or mathematics, we wouldn't want to use implicit differentiation in some circumstances. So it'd be rather pleasurable to actually treat the other variable as a constant. So what we're doing is that we're taking 5xy and we're treating y as a constant. Since y is a constant, we can just treat 5 as the same as y. So which means that when we take the partial derivative of 5xy, what's the partial derivative of 5yx? Because we're treating 5y essentially to be one constant, but they're multiplied together. So the derivative of x is essentially just 1. And since the derivative of x is just 1, then 5yx, if we just have the derivative of 5x, we would obviously get 5. So the derivative of 5yx or 5xy will just be, and we have to do partial differentiation, will just be 5y. Okay, so that's just a short summary of what partial differentiation is exactly it. Okay. So now that we talked about what partial derivatives is, we just have to have a quick recap on the formalism of vectors. I made a lot of videos on vectors, so if you want to learn more about what a vector is and essentially how vectors are essentially formed on graphs and other things, please visit my video on vectors. Okay, now we have to talk about how to write vectors in two different ways. The first way is to write it like this, over here. We can write it in the column vector form, where we have I hat, j hat, and k hat. Notice that I hat, j hat, and k hat are essentially unit vectors in every direction of essentially a 3D space. So if we take a 3D space, the unit vector going in the x direction is I hat, the unit vector going in the y direction is j hat, and the unit vector going in the k direction is going to be, or the z direction is essentially k hat. So that's essentially what I hat, j hat, and k hat are. So we're essentially just writing the specific terms over here. But notice we can also write it another way. We can write it, let's just say, I hat plus j hat plus k hat. And this would equivalently represent this vector over here. And it's essentially aesthetically pleasing to view it as this, because normally when we take the dot product of two vectors, we would write it in this form. But remember that since the divergence is essentially in a partial derivative form, then it's going to be harder to visualize, and it's better to actually write it like this. Okay, so now that we have talked about how to write vectors in two different ways, let's actually start talking about how to take the divergence of essentially a vector. So we need to talk about what the divergence is. The divergence is essentially the partial derivative with respect to x, the partial derivative with respect to y, the partial derivative with respect to z. Now, I've already talked about this in my previous video, but today we're going to actually be talking about how to solve this problem. Okay, so this is essentially the divergence. We want to take the divergence with, let's just say, a random thing, so 5x, 5y, and 5z. Now this would be very easy. We would just have partial over partial x times the dot product of 5x. We will just get 5, 5, and 5. And we have to add them since they're the dot product. So we get 5 plus 5 plus 5, which would essentially be 15. Okay, so that's essentially what we would get if we just take the divergence of this. Now, since we just have essentially a degree 1 for this variable and we don't have any other variables over here, then essentially we're just going to get a specific numerical value. But that's only in this case. In this problem, which you're going to be doing right now, in a minute, we're going to essentially have a specific thing with variables, a specific expression with actual variables inside them. Notice that we have 15 as the answer over here. 15 just tells us that this is going to be a source. In the world of vector calculus, when we take the divergence of a vector and we get a positive value, we consider it as a source. If we get a negative value, we consider it as a sink. Okay. Now let's actually start to solve this major problem over here. So, the first thing we're going to do is write it in another formalism or another way to write the vectors, as I mentioned a little while ago. So, we're going to write it like this. Partial over partial x, comma, partial over partial y, and then partial over partial z. Notice we can also write I hat, j hat, and k hat over here. And we're going to essentially take the dot product with this vector, but we can replace these essentially with pluses. Now, taking the dot product with y tan squared x I hat. So let's just write this below this. So we have y tan squared x I hat plus, or minus in this case, minus 4z squared j hat plus the natural log of y times z k hat. Okay, so we're taking the dot product of these two vectors. So let's just do it. So all we're doing is just taking the partial derivative with respect to x of the first term. Y tan squared x. Well, obviously, we would essentially get y we treat as a constant times, we can write it this way, tan x squared. Now, obviously, in this specific way to write it, we can see that we have to apply the chain rule, which you would get y times 2 tan squared x, well, not squared, we just have raised to the power of 1, times the derivative of the inside. Well, the derivative of tangent of x is just going to be secant squared of x. So we're going to have 2y tangent x times secant squared x for the first essential term. So we can write it over here. 2y tan x secant squared x. Now we have to add it with the next term. Well, we actually don't even have to compute the next term. The reason is because we have minus 4z squared, essentially in the y direction, or j hat, and we're taking the partial derivative with respect to y of a term in terms of z. So which essentially means that when we take the partial derivative with respect to y of minus 4z squared, we're going to get 0, because there's no y variable in that term. So we can obviously say that we're just going to get plus 0, or you could say minus 0 in this case. Lastly, we just have to compute this last term. And likewise in the first term, we just essentially have to use the chain rule again. Okay, so we're going to have the natural log of xy. We're going to take the partial derivative with respect to, this is actually yz. We're going to take the partial derivative with respect to z. Okay, so we're going to take the partial derivative with respect to z of the natural log of y times z. What are we going to do? Well, first, we're going to essentially change it to 1 over yz. Obviously, because if we have the natural log of x, this is just going to be, if we take the regular derivative, we get 1 over x. Simple. But this is not the true answer. We have to multiply by the partial derivative of the inside. If we do that, we get essentially just y. So if we have y over yz, this is essentially just 1 over z. And therefore, this is going to be our answer. So we just get adding 1 over z over there. So now let's just actually write this clearer. We get 2y tangent x secant squared x plus 1 over z as our answer. Okay, so now that we have just taken the divergence of this very complicated looking vector with trigonometric functions inside it and even a natural log function, and it actually seems very easy, we can now talk about the no magnetic monopole rule. So what is the no magnetic monopole rule and where does it come from? Well, the no magnetic monopole rule is essentially one of the laws in Maxwell's equations. So there are essentially 4 equations in Maxwell's equations, or there are 4 laws specifically. The magnetic monopole rule involves the divergence. Now, there's another one that also involves the divergence, but the magnetic monopole rule is very important. Notice that the divergence, we always take the dot product. We don't take the cross product or don't even do any product. We have to take the dot product of the del or nabla symbol. Okay, so what this essentially means is if we take the divergence of essentially a magnetic field, we get 0. Now we know that positive means it's a source, negative means it's a sink. Then what does it mean to be 0? Well, essentially with all our intuition that we have developed over doing this problem and essentially looking at the basics of what the divergence is, we can actually comprehend what this means. We're saying that if we take a magnet, the essential field goes out, but also goes in. So it's going like this. So if you've seen a diagram of a magnet like this, it's going out, but then it's also coming in. So a magnet always has a north and a south. So we can see that there isn't just a complete source. So this is a source, nor there is a complete sink, because this is also sink. We have a sink and a source, because this is going in, this is going out. And if there's a source and a sink, which means it's going to even out, this is going to become zero. So the divergence of the magnetic field must be zero. So there's no magnetic monopole in which the magnet can only be a source or it can only be a sink. So that's what the magnetic monopole rule means, hence the name monopole. Okay, just a reminder, when we have essentially a B with an arrow on the top, or the vector B, this means the magnetic field. If we have E with the vector on top, this is the electric field. Okay, now let's summarize. So in the beginning of the video, we talked about what the divergence is. It measures the source or the sink. The source means essentially the vectors come out or outwards. A sink just means they go inwards. So that's what essentially the divergence is measuring. Then we talked about the basics, or the things we need to know before we actually talk about the divergence. The first thing is partial derivatives, because without partial derivatives, the divergence would be nearly meaningless, because the divergence involves a lot of partial derivatives. In partial derivatives, we always treat the other variables that we're not taking the derivative with respect to as constants. It's way different than implicit differentiation. After that, we essentially talked about how to solve a regular or a very simple essential vector, and we're taking the divergence of a vector. And it was very easy. We just take the dot product of the partial derivatives and we essentially take it with the vector. And we also talked about a very important thing of how to write vectors in two different ways. The first one is the normal way we write a vector, over here. The second one is essentially how we write it in component form, with I hat, j hat, and k hat, unit vectors in the x, y, z directions. After that, we actually tried solving this problem. Notice that partial derivatives are very crucial, because once we solved this problem, we got this: 2y tan x times secant squared x plus 1 over z. After that, we talked about the no magnetic monopole rule and how we can apply our intuition that we have developed over this course of the video to actually understand what this rule means. And notice that this is actually a physics concept in electromagnetism. Now that we have summarized, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.